Okay, and we're back. This is part 2 of the video. So if you've got propene, it's going to be like this, isn't it? So there we go. And it's going to be an H up there and a CH3 there. Now, if you know your Markovnikov, the hydrogen is going to add to this one and the chlorine is going to add to that one. So the major product is going to be 2-chloropropane. Whoops. Nice of us about propane. Okay, so 2-chloropropane is going to be the major product there. Why is that the case? Why do we get that? Well, obviously it's Markovnikov's rule, isn't it? All right, but why does Markovnikov rule work? Is because if to get the 2-chloropropane, it goes through, a secondary carbocation. All right. Now, if it goes through a secondary carbocation, which is more stable, than the primary carbocation, which you'd get if it was which 1-chloropropane would go through. Okay. So basically you get the 2-chloropropane because you get a secondary. Now, if you can remember your chemistry, your organic, let me get rid of that. All right, and that means you get the secondary carbocation there. All right, and that's more stable than the positive on this one, which would have been the primary. Right, an equation for the reaction of the major product with aqueous sodium hydroxide. All right, so now the major product is CH, what is it? CH3, CHCl, CH3. In other words, the 2-chloropropane. If we react it with sodium hydroxide, it's going to be a substitution reaction, and the CH3, CHOH. The OH is going to take the place of the Cl, CH3 plus NaCl. Okay, there you go, piece of cake. All right, so there, piece. That's nice and easy. That's just a reacting with sodium hydroxide, and the halogen alkane turns to the alcohol. All right, let's have a look at the next one. This one looks like a rate question. Let's get all of it. I didn't realize it was going to be this long, guys. I'm sorry. All right, I didn't want it this long, but never mind. Right, there we go. All right. An experiment was carried out to determine the order of reaction. Between that isomer, the following results were obtained. Determine the rate from the results explaining the rate expression. Okay, so let's have a look at 1 and 3. In other words, this is the same as this, and we're timesing that by 3. Okay, what happens to this? We're timesing that by 3 as well. So therefore, it is first order with respect to the C3H7Cl. Concentration of that. Why? Because from experiment 1 and 3, we times the concentration, the conc was times 3, and the rate was times 3. So therefore it's first order using those two. Let's have a look at the other ones. Now let's have a look at this one, 1 and 2. All right, let's get the calculator out here to see the conversion factor, the rate factor. All right, so we've got 1.3 exponential minus 3 divided by 3.1 exponential minus 4. So that is going from, where are we? 1.3. Going from there to there is an increase by a factor of 4.2, about that. This is times 2. This we already know we're timesing it by 2. It's first order, so that's times 2. So it must also be first order with respect to that. So first order with respect to the OH minus ion. Oops, that goes in there, not there. All right, now I'll explain that again, because from equations from experiments 1 and 2, we double the OH concentration and the rate doubles. Okay, now it doesn't double, does it? It goes up by a factor of 4, but don't forget this is doubling as well. So this change from there to there is a doubling, and so that's going to affect the rate by times 2, and therefore this doubling is going to affect it by the other times 2. So it's first order with respect to both of them, and therefore the rate equation is going to be OH minus times this guy, C3 H7Cl, and that's the rate equation, first order with respect to both of them. Okay, I hope that makes sense. This one is pretty tricky, isn't it? All right. So there you go. I hope that makes sense. Did you use the type of mechanism for this reaction of the isomer of that with sodium hydroxide? Well, the mechanism, because it's got 2 things here, 1 thing, 2 things, it's second order, isn't it? All right, so the mechanism must be a nucleophilic substitution biomolecular. It must be an SN2 mechanism. Sketch the mechanism. All right, so this is going to be an SN2. All right, SN2 is this. Let's have a look. It's CH3. Then we've got a CH, and we've got a Cl here. And we've got a CH3 here. So what happens is my OH minus comes in. Okay, the OH minus comes in, attacks there, and at the same time this starts to leave. So we get this intermediate, don't we? We get the CH, CH3, CH3. This thing is coming in, and this thing is leaving, and then this eventually leaves, and we get OH, CH, CH3, CH3, something like that, and a Cl minus ion. Learn your mechanisms. That's all I've got to say there. All right, if you need help with them, please ask. But this is a classic SN2 mechanism. All right, now I think we'll finish at number 3 because this is going on for way too long. All right, I don't know, was there a number 4? Oh God, it goes on forever. All right, this is still number 3. There we go. It's way too long, this one, isn't it? Write an equation for the complete combustion of that. All right, well, that's not a hard one, is it? So I'm cheating. I'm just looking at answers, but it's straightforward, isn't it? 2C3H8O plus 9O2 is going to give me 6 carbon dioxides plus 8 waters. Okay, you should put the state symbols in. So that's a liquid, there's a gas, that's a gas, and that's going to be a gas. It's going to be formed as a gas. All right, so that's the complete combustion. That's a straightforward one, though, isn't it? Determine the enthalpy of combustion using data from section 11. All right, so what we've got to do now is we've got to figure out which bonds are broken and which bonds are made. Now, this is tricky, okay, and I think the best way of doing it is drawing the thing out. Okay, OH, H, 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 H. Oh my God. So 1, 2, 3, 4, 5, 6, 7. So we're going to break 7 CH bonds. We're going to break a CO bond. And we're going to break an OH bond. We're going to break all of those bonds. I think that's it. Oh, and we're also going to break 2 CC bonds, aren't we? 2 CC bonds. I think that's the lot. We've also got to break those, haven't we? So there's 9 of those. So I'm going to break 4.5 OOs. Because we're figuring out the combustion of 1 mole of this, and this is 2 moles. So we're going to split that up into 2. Okay, so according to the data booklet, you add all those up and you get 6652. What do you form? Well, you form CO2. CO2. So what you form is 1, 2 times 3, 6 CO bonds. All right. And you'd get 8 times 2, 16. But we're dividing everything by 2, so that's 8 OH bonds. So that gives us, according to this, 8528. This is endothermic, this is exothermic. You add these two together and you get minus 1876 kilojoules per mole. It's just an accountancy one there, isn't it? State the reagents for the conversion of this, which is a secondary alcohol, into C3H6O. So what we're doing there is we're converting it into a ketone. So we start off with this secondary alcohol. Okay, and the only thing you really do with this is you can oxidize it to the ketone, which is this. Okay, and that's what you got to do. And how do we do that? Well, we use acidified potassium dichromate. Okay, so we heat and we use acidified potassium dichromate. Okay, and there you go. All right, simple as that. Okay, next one. Yeah, have we got any more? Yeah, this is the last one we'll do because this was going on for way too long. Explain why a compound that produced the amount was a higher bonding point than that. Well, the first compound is a alcohol, as you know. So this guy is propan-2-ol. Propan-2-ol is an alcohol, obviously, and it will form hydrogen bonds. All right, which are stronger than now this guy is going to form dipole-dipole interactions. Dipole-dipole interactions. Okay, so there you go. So that's the deal there. All right, let me stop here and I'll finish it off another time. This has gone on for way too long. And if you're still with me, well done. All right, thank you.